Okay, good morning, everyone. Sharing the screen. Oh, only Anirudhan has come so far. Okay. All right. So we will wait for a minute or so. Okay, let's get started. So we were looking at this function mx. That is basically the regression, or rather the conditional expectation of y given capital X equal to small x. That is the function. So that is what we had denoted by m at small x. So we had shown earlier that this x going to mx is a proper measurable function. So it makes sense to talk about the composition of the random variable x and m. And we have also seen that that is a real valued random. Yeah. So we had seen that this m composition x is a real value random. Okay. Now, based on that, we are, as we had done in the discrete case, we are going to call this m of capital X as the random variable conditional expectation of y given x. So defining formally, let xy be a two-dimensional continuous random variable, and expectation x, let's say expectation y exists. Then this random variable conditional expectation y given x on the basic probability space is defined by this. So this random variable is of course called the conditional expectation of y given capital X. If you want to note it down, please do. Sorry, yeah. So this is a result which one would be expecting, because that is what we had done in the discrete case, and we have also alluded to this earlier in one of the exercises, if you recall. Yeah. This is what we had got here. And that proposition is basically a restatement of this part 2. Right. So expectation of the random variable conditional expectation y given x is precisely expectation of y. So you can verify formally. This is by definition, and this is because, again, because of definition of expectation of a random variable and so on. And recall that here this f sub x is the PDF of the random variable x, and then you have this. It's a fairly simple proposition. Okay. Note it down if you want to. Yeah. And I'm going to state two other results, whose proof is just as in the case of the discrete case, replacing the summation by integration at appropriate places. So we will not look at the proofs. These are exercises. The first result basically says the conditional expectation operation is a linear operation. Namely, if you have x, y, z as a three-dimensional continuous random variable, such that expectation of y and expectation of z exist, then for any constants a and b, real constants, conditional expectation of ay plus bz given x, is a times conditional expectation y given x plus b times that given, or that of z given x. And since the two objects on the right side make sense only when these guys exist, that is why this made as an assumption. So the next is, let xz be continuous random variable. G is a real valued function on the real line, such that gx, z is also a continuous random variable. And suppose expectation of z as well as expectation of the product of this gx and z exist. So because of this assumption, the left side here makes sense. And what this says is, since gx is a function of x, that sort of behaves like a constant, and that can be pulled out of the conditional expectation operation. Again, something similar we have done in the discrete case. Not similar, exactly the same. You may note it down. Okay. So using measure theory, this is for those who are familiar with measure theory. Aniruddhan, you have done measure theory, right?
Yes, sir.
Yeah. So I will give you a reference where you can find these things. Using measure theory, the notion of conditional expectation of y given x as a random variable can be defined for general random variables. Actually, there the conditional expectation would be defined as a conditional expectation of a random variable given a sub-sigma algebra. I mean, those of you who have not done measure theory and who have come to this class now, please you can just listen to it. You may not be able to make out much, but so there, what one does is to sort of relate that kind of a definition to this, you take the sub-sigma algebra as the smallest sigma algebra with respect to which x becomes measurable. Basically, that will consist of x inverse of Borel sets. And the smallest sigma algebra containing x inverse of such sets would be the smallest sigma algebra with respect to which x is measurable. So that will be sigma algebra in your basic space omega.
We touched upon this in our measure theoretic probability course.
Pardon?
We touched upon this in our measure theoretic probability course.
Conditional expectation also you did?
Yes, yes.
Oh, okay. So then you already are familiar with it. Yeah. And did you also do that if something about what happens if these things are square integrable?
They stay in the same space. Is that what you're talking about? The conditional expectation also stays in the same L2 or L1.
Of what? L2 or L1 of what?
of the same omega.
No, that is right, but that is rather obvious. But the thing is, okay, since you have already done it, but anyway, I'll give you some references. Did the B. Vigaro give any reference for these things?
No, we majorly used his notes and
Billingsley's book and things like that, I suppose.
Okay, I'll check it out.
Yeah, it doesn't matter. And so, are you taking a course in functional analysis?
Yeah, this time I'm taking graduate analysis too.
I mean, is functional analysis part of that?
Yes.
Functional analysis, but I mean, for example, one of the most important class of spaces you will come across in functional analysis is L2 of R or L2 of omega or LP of omega and things like that.
Right.
Have you come across such objects?
We kind of touched upon it in our graduate analysis 1 course.
Yeah. I mean, this will turn out to be LP will turn out to be a Banach space, and L2 will be a Hilbert space.
Yes.
Okay.
Yeah.
So if your random variables are square integrable, then if you take, let us say both x and y are square integrable. Let us say x is an element in that space. Then you take the smallest sigma algebra with respect to which x is measurable. Your L2 space is L2 omega script A P, right? A is a subsigma of the sigma algebra. If you take a subsigma algebra, let us say, which you denote by sigma within brackets x, that is sigma algebra generated by x, that would be a subsigma algebra. Then L2 of omega, that sigma xp in itself is a Hilbert space, or rather subspace of the big space. So the conditional expectation will turn out to be the projection of this vector y onto the subspace, onto the onto the subspace.
Right. Okay.
So this kind of idea you will see will play a role in something which we will do in the next class.
Okay.
So these kind of objects can be defined for any general random variables. Need not be discrete, continuous. They may be both, mixture of both, or neither, and so on. So in that case, the requirements like this, the previous proposition, need not be assumed. Just integrability, this would do. This exists would do. One doesn't have to assume such things. Here we are assuming because we have done all these things in the framework of continuous random variables. So in particular, so if you have things like that, then one can talk about conditional expectation of gx given x, and of course, in particular, conditional expectation of x given x. Those things are these, so these identities also hold. Okay. So heuristically, when conditioning on x, we view x as a constant. And hence, gx can be brought outside the conditional expectation. That is what this result means. Of course, if g is a bounded function and expectation z exists, then you know that expectation of gx multiplied with z always exists. Okay. Now let us look at an example. So let the function f be f1 r2 be given by this. F at xy is √3 divided by 4 pi e to the power minus half times x squared minus xy plus y squared for all xy. You may easily, you may be sort of having a guess that this is a kind of bivariate normal density. I mean, you might have even come across an example like this. So verify that this guy is a genuine two-dimensional PDF. So there is a two-dimensional random variable xy such that f is the PDF of that xy. So the marginals are this. And from this, you can easily make out the marginals are basically the normal densities with mean 0 and variance 4 divided by 3. From here, you can make out that. Also, it is easily seen that x and y are not independent random variables. It requires some more effort to verify that covariance of x and y is 2/3. So verify that xy is a random variable having the bivariate normal distribution with mean vector 0 and covariance matrix big sigma, capital sigma equal to that. So the variances are here on the diagonals and the covariances are here. So now next step is you can verify that the conditional PDF of y given x equal to little x is this. Here, note that x, so the role of x is like a constant. So this is a one-dimensional PDF, which turns out to be again a normal density, now with mean half x and variance 1. Yeah. Of course, verification of these things are very simple. So the conditional probability density function of y given capital X equal to small x is the same as the PDF of the normal distribution. So it follows the conditional expectation of y given x equal to little x is precisely the expectation of such a random variable, which is half x. Consequently, the conditional expectation as a random variable, of course, you just have to substitute this little x by capital X. That is our standard trick. or standard recipe. So that random variable is half x, which is a linear function of x. So in this case, the regression function is a linear function. So suppose x and y are independent continuous random variables, and let expectation y exist, then the conditional expectation of y given x is expectation y itself. I mean, expectation of y. It's a constant. So it is not a random, and this conforms to our intuitive notion of independence. Of course, this also holds for general random variables. Because in that case, that the L2 projection will be onto the subspace generated by the one-dimensional space generated by the constraints. Yeah, let's note it down. Okay, let xy and x tilde y tilde be two-dimensional continuous random variables. Such that the distribution of x tilde y tilde is the same as the distribution of xy. And the usual notation is equality in distribution. So you put an equality sign, and over that you write small d. That means equality in distribution. So probability, let us say x tilde y tilde belonging to a rectangle in R2 will be the same thing as the probability of xy taking values in that same rectangle for every rectangle, or rather for every Borel set in R2. These objects may be random variables on the same space, or might even be different spaces. It doesn't matter. You can even consider without laws of generality, same space, because otherwise you take a product. Product space. So therefore, the density functions, PDFs of x tilde y tilde will be same thing as the PDF of xy. So would be the marginals. And also the range of x tilde and the range of x would be same. And the expectation of, for example, y tilde exists if and only if the expectation of y exists. And similarly for x tildes and x. So it follows, I mean, from this, first of all, you will have that the conditional PDF of y given x equal to little x will be the same as conditional PDF of y tilde given x tilde equal to little x. It's the same little x, because that has to be in the R. I mean, from these equalities, you immediately see that the conditional PDFs should be same. So let x1 and x2 be independent, identically distributed, continuous random variables. And both have finite expectation. Then the conditional expectation of x1 given x1 plus x2 is the same as the average of the sum. See, note that this is going to be a function of x1 plus x2. And what kind of a function? Since x1 and x2 are IIDs, then there is really nothing to choose between them. So it would be half of the sum. That's a natural guess. So this is a guesswork. Well, how does one prove it? So for proving that, we make use of this remark. So note that x1 plus x2 is same thing as x2 plus x1. So the hint is they are identically distributed, independent, identically distributed random variables. Therefore, x1, x2 will have the same distribution as x2, x1. Then take this linear transformation on R2. U, v going to u, u plus v. You can easily figure out the matrix corresponding to this linear transformation. And you will see that that is non-singular. So now under this transformation, x1, x2 will go to x1, x1 plus x2. So that is T of x1, x2. And that the distribution of that is same thing as distribution of T of x2, x1. Because x1, x2 and x2, x1 have the same distribution. And this precisely is x2, x1 plus x2. So use the remark and also use the fact that which was another exercise, that conditional expectation is a linear operation. Well, that comes to the end of today's thing. So is there anyone who has not done measure theory in the audience? How many have come today? I'll stop sharing. Krishna Gupta, name is, this is, I'm not familiar with this name. So this, have you done a measure theory, Krishna Gupta? Oh, you have not done measure theory. Okay, have you done stochastic process 1? Okay, but you may be knowing that stochastic process 1 is prerequisite for enrolling in this course. Of course, I don't mind you are attending lectures and so on.
Yes, sir. I have done a similar kind of a course in my bachelor's.
But unfortunately, it should be, if it is not SP1 or something eco, I mean, something like, I mean, in CMI, because that we have put as a prerequisite, I don't want to change it.
Okay, okay.
However, you can attend the lectures and also the notes whenever they are put up on this thing, you can make use of them and so on.
Right.
So this is just that there is no misunderstanding about enrolling for the course.
Okay, okay.
So since you have not done measure theory, you want me to go over some of the slides today again? Since say I had prepared the things and also I wanted to go at a pace so that people who have not attended measure theory also would be able to follow. But since the other person has done measure theory, I might have been a bit fast. So if you want, I can go back.
No, sir, like today it was fine.
You could come and get the feel of the whole thing, right?
I could follow, but sir, I couldn't attend the first lecture.
Oh, first lecture you could not attend. Okay, let me see. That in today's this thing itself, I can, since it is a continuation, I can go back to that.
So sir, I just wanted to ask if you like upload these lectures, the recordings and the notes.
Pardon?
If you upload the recordings on Moodle.
Yeah, this thing is put up in the Zoom, no? That YouTube.
Okay, so I couldn't find the link for the first lecture.
Oh, I see. You enrolled as a participant after our first lecture?
Yes, sir.
But anyway, today's when that link comes,
okay, I get the playlist.
This is part of this also same thing, okay? Because it's the same file. So
okay, I think Aniruddhan has put it up in the comment section, so I'll take it up from there.
Okay, okay, yeah, yeah. And that is basically recalling, continuous random variables.
Okay, okay.
So you are in which class in CMI?
Data science.
Which BSc third year or?
No, MSc first year data science.
Oh, so last year, rather you did not take SP1, is it?
I'm in the first year. Earlier, I didn't did my BSc from CMI.
You did your BSc from CMI?
No, I didn't do my BSc from CMI.
Oh, you did not do. Okay.
Yeah.
But you are.
I was. This is not basically my core subject for MSc data science. I'm just having a look at the.
Oh, you are in MSc
syllabus.
data science?
Yes, yes.
But MSc. Oh, you are MSc data science first year.
Yes, sir.
Okay.
I'm like looking at the subject before I enroll, so I'm not like thinking of enrolling right now. I'm just having a look at the.
Perhaps testing the ground for next year.
Yes, sir.
Or next semester, something like that. Okay.
Right.
Yeah. Anyway, so I appreciate your curiosity, but I hope this will not affect your.
I'll consider everything before enrolling formally for the grade part.
Yeah. So concentrate more on things which you will be taking the things. You did BSc in maths or
statistics.
Statistics. Okay. So of course, for the first semester for math analysis and probability courses will be fairly easy for you. And I don't know
Right.
about the computer related courses. So anyway, it's
Yes.
all up to you. Where did you do your BSc from?
Delhi University.
Delhi University. Very good, very good. So there, they have a separate stat department, right?
Right. Sir.
Okay, good. Okay, good luck.
Thank you.
So today you don't want me to go over anything. That's fine.
Right.
So in that case, stop sharing. I don't know how it's worked out. Okay, good. So Aniruddhan, again, like last semester, the attendance seems to be very thin.
Yeah, that's well. I attend the classes nevertheless.
Yeah, okay, good. So even if an audience of 1 or 2 who are quite keenly following, I don't mind. Okay. So
Maybe once registration is over, we'll have an idea of how many are crediting the course.
let us see, because the number of participants seems to be slightly more than 20. So anyway, okay. All right. So let us set that. I mean, since I didn't expect, I thought there will be at least few people who have not taken measure theory. So I went quite fast today. Maybe that's okay. So we will meet next time. So till then, take care, both of you. And yeah, we will meet on Monday. Okay.
Goodbye, sir. Have a nice weekend.
Yeah, you too.